So this is part 2 of a motion graphs video. In part 1, we looked at position time graphs and velocity time graphs, and the last thing we saw is that displacement can be calculated by finding the area under a velocity time curve. So here's a velocity time curve. The area below it is going to be down here, right? So for some interval t1, t2, that's what the area looks like. If you find what it equals by finding the area of the triangle and then adding the area of the rectangle below it, then that area equals the displacement for that interval. Right? So here's an example. We haven't proved that this is true, but what I'm going to do is take a kind of simplistic example and show that this area under the curve method gives you the same answer that you would get if you use the kinematic equations, which we also call the Suvat equations. So we have an object moving at negative 10 meters per second. It accelerates for 8 seconds uniformly, constant acceleration. And at that point it's reached a speed, a velocity of positive 10 meters per second. What's its displacement? Well, it starts down here, which is negative 10. It ends at 10, positive 10, and it's had some displacement. So we're given that this time, I'm going to call this t2 because I want to make sure I mark this one as well. That'll be important. This time, which I'm calling t2, is 8 seconds, right? And that's the time at which it's reached positive 10 meters per second as the velocity. And because this is constant acceleration, right? Because it's a straight line, constant acceleration, constant slope, we know that this value, right, if this is 10, and if this height is 10, and it's a straight line, then this is the midpoint between here and here. So if t2 is 8 seconds, then t1 is 4 seconds. We could prove that using the equations and some geometry if we wanted, but this kind of rough explanation will suffice. So at this time, t2, 8 seconds, we have reached a speed of 10, positive 10 meters per second. It's not shown just because I was running out of space. Down here, the starting velocity is negative 10 meters per second. Right? So this area, delta x1, is the area under this part of the curve. And we find that, let me hold off on the equation. We find it by calculating the area of this triangle, right? Area of a triangle is 1/2 base times height. So the base is from here to here. That's 4 seconds. 4 seconds. 1/2 base, 4 seconds. For height, we plug in the height, which is negative 10, right? This is negative 10. And it has units of meters per second. This has units of seconds. And what we get is negative 20 meters as delta x1. That's the area under the curve, and it equals the displacement. Delta x2 is what we're going to look at next. We use the same exact formula because we have a triangle. That's the shape formed by the area under this part of the curve. So we have 1/2 base height. The base, again, is from t1 to t2. That length is the base. And if this is 4 seconds and this is 8, then this is 4 seconds. So you plug in 4 for the base. The height of this triangle is from 0 to 10, positive 10. Before it was 0 to negative 10. Now it's positive 10 as the height, so we plug it in. We use include our units, and we get positive 20. Right? So that gives us the displacement for the first segment, the first 4 seconds. And delta x2, this second equation, gives us the displacement for the second 4 seconds. Let me say, the last 4 seconds, right? From 4 seconds, t equals 4 seconds, to t equals 8 seconds. If we wanted the total displacement for the entire trip from 0 to 8 seconds, right? 0 to 8 seconds, we just add the two areas under the curve, and we get negative 20 plus 20 is 0. 0 displacement, right? And intuitively that makes sense. If we start at some negative velocity, and we accelerate until we reach the positive equivalent, then what we're kind of doing is we're going backwards and then going forwards, right? So this makes sense if you think about throwing a ball. If you throw a ball up with some initial velocity of 5 meters per second, then when it returns to your hand, it's going to be going at 5 meters per second, but down instead of up, thanks to the symmetry of its up and down motion. So the same sort of logic applies here. Okay, now we're going to look at the last thing, which is acceleration time graphs. So on an acceleration time graph, we put acceleration now on the y-axis. So we've seen three types of motion graphs: position time, velocity time, and acceleration time. Now, if an object is getting, if the curve, the AT curve, is getting farther and farther away from the x-axis, right? Well, now the x-axis represents the value a equal to 0. So whenever we're on the x-axis, we know the acceleration is 0. And if we're moving away, the acceleration is growing in magnitude. Right? Here the acceleration is getting more and more positive, getting bigger in magnitude. Down here, the acceleration is getting bigger and bigger in magnitude, right? This is an acceleration of 2 meters per second squared in the negative direction. This is 8 meters per second squared in the negative direction. I'm making those numbers up. They could be anything. So the magnitude is increasing. It's just that that's a magnitude which is going in the negative direction down here. So the magnitude is still increasing here. The value is still increasing. It's just that it's increasing in the negative direction. And it could be curved, and the same thing would apply. The magnitude is still growing. Okay. And like we were saying, whenever we pass through the x-axis, or whenever we're lying on the x-axis, right, any curve on the x-axis has an acceleration of 0, because the x-axis represents that value, a equal to 0. Even if we just pass through the x-axis momentarily, we have acceleration of 0. And for those two segments or portions of this curve, the velocity is constant, right? So for this period, the velocity is constant. For this brief moment, right, for that very, very brief instantaneous moment, the velocity is constant. But here's the thing. The velocity, being constant, it might be a non-zero velocity, or it might be a zero velocity, a constant velocity of 0. So just because acceleration is 0, right, in both these cases it's 0 acceleration, we don't know definitively from this graph alone if the object also has 0 velocity or simply has some other constant velocity. Right? We can't tell, because all we know is that it's not accelerating. So an object standing still is not accelerating. That could be what's happening here. But an object that is simply moving at 10 meters per second, a constant velocity of 10 meters per second, also is not accelerating. So this flat line doesn't tell us which of those two options or possibilities is occurring. Okay, if we have a flat line above or below the x-axis, a flat line means we're staying at the same y value, right? And successive points along this line all have the same y value. The y value is not increasing, right? The y coordinate, that y value is not decreasing as we move forward along the line. So the a value, the acceleration, the y value, remains constant. And that tells us that Suvat equations apply. Those are the equations of constant acceleration, Suvat. Right? So they apply. And in this case, we have positive acceleration because the value of a is in the top half of the y-axis. So it's some positive value. It's up here above 0. If we have a line down here below a equal to 0, then that's obviously going to be constant acceleration in the negative direction. So constant negative acceleration. And in both Suvat equations do apply. We can use those. So we said before that the area under the VT curve gives us displacement, right? Because V times T is displacement. If we take A and we multiply A times T, what's happening to the units? Well, A is meter per second squared, T is seconds, and the product of those gives us meters per second. So what this turns out being, and we could prove it with calculus, is that the area under an AT curve, right, maybe this area or this area or this area, or maybe all three, so that we're looking at the area under the whole curve, that area gives us the change in velocity during the time interval that we're evaluating. Right? So during this time interval, this is the area under the curve, and that tells us, if we calculate that area, right, by reading off the tick marks and finding the area of this triangle and adding the area of the rectangle, that area gives us the change in velocity during this interval from here to here, that time interval defined by time. So here's an example of an interval, t1 to t2. We trace up, right? We see that this is a convenient interval to consider because it's just a box, a rectangle. So that area gives us the delta v, the object experiences between these two times. Right? And clearly here the area is positive because it's on the top half of our graph. It's above the x-axis. So the change in velocity then would be positive. Down here the change in velocity is negative. It's losing velocity or decreasing in velocity. Right? So it can be positive or negative, that area. Delta v is the change in velocity.